When you settle into a window seat, the experience of commercial flight feels remarkably serene. You feel the thrust, the liftoff, and then a smooth, quiet ascent as the Earth falls away below you. But outside that thin plastic window, the environment is physically violent. The metal skin of the aircraft blasts through sub-zero air at 500 miles per hour, acting as a pressurized balloon holding back an atmosphere that is actively trying to rip it open. Looking at this cross-section of two fuselage panels under simulated air pressure, we can see the immediate threat. At 30,000 feet, even a sub-millimeter gap between these panels, or a single misaligned rivet, allows internal pressure to wedge into the seam. The extreme pressure differential causes that tiny gap to expand, tearing the metal and leading to rapid decompression. The engineering miracle occurs on the ground, where the flawless physical assembly ensures a failure never has the opportunity to begin. To achieve that level of precision, you have to enter an environment built on an entirely different scale. Inside these assembly facilities, the fuselages look like sleeping whales, and the human engineers walking between them are dwarfed by the operation. It creates an immediate physical paradox. The factory relies on heavy industrial infrastructure, cranes, scaffolding, and machines the size of skyscrapers, to execute tasks that require the delicate precision of a watchmaker. Managing this paradox requires an engineering discipline called kinematic tolerance. This is the science of maintaining microscopic exactness across massive, heavy parts while they are in motion. To build the safest transportation on Earth, aerospace engineers first had to invent manufacturing equipment that violates our basic human intuition about how heavy objects behave. Before an aircraft is fully assembled, its isolated components require a massive footprint of their own. A single commercial wing spans dozens of feet and takes up the floor space of a small house. Once fully constructed with its internal fuel tanks and skeletal ribs, that wing weighs upwards of 50 tons. Moving an object that heavy across a busy factory floor is a hazardous operation. The industry solves this using automated guided vehicles, or AGVs, low-profile robotic transport platforms designed to slide underneath these multi-ton payloads and carry them between assembly stations. But lifting the wing is only the first step. If an AGV carrying 50 tons of forward momentum hits the brakes too quickly, the resulting shockwave would rip through the wing's internal skeleton, inducing microscopic structural fractures before the plane ever leaves the ground. This simulation demonstrates how the transport systems manage that momentum. Active hydraulic dampening systems are built directly into the AGV. As the vehicle decelerates, these systems absorb the kinetic energy of the moving wing, transferring the shock into a fluid system that dissipates the force safely. Because the dampeners erase the physical shudder, the robotic vehicle parks its 50-ton payload within a margin of error of less than 2 millimeters. Massive brute force only becomes an asset in aerospace manufacturing when it is neutralized by perfect algorithmic control. That same control governs the rapid movement of the automated assembly arms working directly on the fuselage surface. These industrial robots swing through the air only to snap into a dead, perfectly still stop millimeters above the metal. They are built for speed. Automated riveting machines punch holes and secure fasteners at a rate of thousands of repetitions an hour, locking the airplane's skin to its internal frame. But all that rapid, repetitive friction generates heat. The localized thermal expansion causes the metal and composite panels to slightly warp and shift, meaning the pre-programmed physical coordinates of the rivet holes are constantly moving. If the robot blindly followed its original coordinates, it would drill directly into the weakened edge of a shifted panel. To prevent this, engineers utilize a closed-loop feedback system. This visualization shows the feedback loop in action. Laser sensors mounted on the tool head constantly scan the shifting, heat-warped surface of the material. They bounce that topographic data back to the machine's central processor, which recalculates and adjusts the drill's physical position in real time. By correcting its own trajectory hundreds of times per millisecond, the machine maintains a target lock even as the material behavior changes. These robots continuously negotiate with the changing physical reality of the airplane, adapting their work to match the material's live state. When a completed aircraft finally rolls out of the facility, it represents the successful alignment of millions of individual, hyper-controlled variables. The finished plane is the culmination of 1,000,000 perfectly choreographed robotic acts, frozen in metal and composite. As we look toward the future of aviation, designers are mapping out radical new concepts. We are seeing blueprints for blended wing bodies that resemble flying mantas and structures relying on ultra-lightweight, continuous carbon composites. The primary limiting factor for getting these designs into the sky is no longer aerodynamics or even physics. The bottleneck is the physical manufacturing capability. Right now, the aerospace industry is waiting on the invention of entirely new classes of machines, tools capable of fabricating these complex geometric shapes with the same microscopic kinematic tolerances we use today. Before humanity can fly the planes of tomorrow, we first have to invent the machines capable of building them.